Bismillahirrahmanirrahim. Welcome back to all of you in this session. And this session is basically the last session of week 1 of CIMPA School 2022 COMSATS University Islamabad Lahore campus. And this session includes the fourth lecture of course 2 by Professor Tomas Vetrik. And I humbly request Professor Vetrik to please start his lecture. Sir, over to you, please.
Yes, sure. Thank you very much. So we will continue with cyclic telegraphs, which I introduced yesterday, and just move this machine. And so I mentioned that the construction which I'm going to introduce is using finite fields. So we know that finite field has, or we also call it Galois field, has two groups, additive group and multiplicative. So we are going to use the symbol F plus for the additive group of the finite field and notation F star for the multiplicative group of the finite field. As you can see, the result which is mentioned here doesn't hold for every value of D. So not for every degree. So again, just for me to remind you the parameters, this CC or the notation, CC means cyclic Cayley graph. So we are constructing cyclic Cayley graph having this number of vertices. Therefore, it's a lower bound. If somebody will construct a Cayley graph, cyclic Cayley graph having a larger number of vertices, then the bound will go up, and so on. So always the challenge is to construct the largest known cyclic Cayley graphs, and always larger will bring the lower bound up. On the other hand, as I mentioned, some researchers are studying upper bound on the problem, means they are showing that non-existence of cyclic Cayley graphs of certain order, of certain number of vertices. Then again, if you want to improve the upper bound, you must show non-existence of slightly smaller number of vertices. That such Cayley graphs of cyclic group can't exist. However, we are studying lower bounds, we are studying constructions, and this is the number of vertices in this construction of cyclic Cayley graphs. Now, look at the degree. The degree is in terms expressed in terms of prime, and now the question is why prime? The point is we want this group to be cyclic, and if you want the direct product of three groups to be cyclic, first property is all of them must be cyclic. Okay, well, multiplicative group of the finite field is always cyclic. Additive group of the finite field is not always cyclic. If you want the additive group of the finite field to be cyclic, it must be of prime order. Okay, therefore P is prime because we want this group to be cyclic. This will be cyclic because P is prime. Therefore, it's defined for primes, but not for all primes. As you can see, some P which are primes are excluded. Why? Because it's not sufficient for these groups to be cyclic, for the resulting group to be cyclic. There is also other thing which must be satisfied. Not only all of them must be cyclic, but the orders of any two of them have no common divisor greater than 1. So it means the orders of these three groups, it's not possible for one number to be divisible by some other number. Therefore, P is not 30. Because if the order of this group would be 30, then you would have 13 here, 13 here. So they would have a common divisor, the greatest common divisor would be 13, and it wouldn't hold. So again, the greatest common divisor of all them must be 1. So it means this one cannot be 13. And now, probably you know that if the order of this group is P, the number of elements in this group is p minus 1, okay? Because it can't contain the identity of this group. So the identity of this one, if it's 0, this one can't contain 0. So again, the number of elements in this group is p, but the number of elements in this group is p minus 1. Therefore, we must have this property. Because if assume this would be a number, let's say, I think 53 is prime, and it's satisfying this pattern, then the number of elements here would be 52, and 52 is divisible by 30. So again, it can't be 1 modulo 13p, because the order of this group, the number of elements, is p minus 1. This group has p minus 1 elements, so this would cause trouble if it would not exclude 1 modulo 30. Okay. If we are satisfying these properties, then this group is cyclic. And we are happy because we want this group to be cyclic. Then we have bound for cyclic Cayley graphs. Cayley graphs which are coming from cyclic. And now we need to find generating sets. Well, the generating sets which are working for this graph are described here. Again, maybe it will be a little bit confusing, but I believe if I explain it in detail, you will understand it. So it will be always unclear why I chose this type of generators, because it was kind of again some deep investigation what works the best. But I want to explain you, let's say, which is easy to understand, why for these generators, these are the inverses. So if you are taking, we need to have notation for the identity elements. So let's have 1 to be the identity element of the multiplicative group, and let's have 0 to be the identity element of the additive groups. We have 2 additive groups. These 2 are our additive groups, and this one is our multiplicative. So the identity of this group will be 0. Also, the identity of this group will be 0. And the identity of this group will be 1. So, for example, here you have 0, 1, 1, which means this one is actually not identity. So, this one is identity for this group, but this one is not identity. So, but this element is just to fix some minor troubles, because it wouldn't work to have diameter 2 if I wouldn't add this element. But the most important are actually these sets of the generators. So, focus on AX, BX1, and CX2. So first, what are the inverse elements for those elements? So if you are taking inverse for AX, inverse element for AX, since this is from additive group, it will be minus X. This one is from multiplicative group, therefore we are using notation X to the power minus 1. And again, 1 is from the additive group, therefore inverse is minus 1. And very similarly for the B elements. So as you can see again, X1 is from additive group, therefore minus X2. This one is identity. Therefore, inverse element is the same, and additive group 3, inverse element minus. Here, similarly, inverse for 0, we are in additive group, 0. Inverse for X2, we are having multiplicative group, X2 to the minus 1. And additive group, inverse for 4, minus 1. Similarly for this. And the generating set has these elements, meaning we know from the previous lectures what's the meaning of the elements in generating set. Every element in the generating set will bring us edge. Okay? So all these elements will give us edges. From every vertex, there is edge going to the other vertices. For this particular X2 is from the multiplicative group, and X1 is from the additive. Now, what is the degree of every vertex? The degree of every vertex is the number of elements in our generating set. Well, let's count all of them. How many of them do we have there? So this is only one. Okay, this is a single element. How many elements do we have here? Well, X is from the multiplicative group, and I mentioned the number of vertices in the multiplicative group is p minus 1. So p minus 1 are the number of elements here. Here we have x1 is from the additive group. So how many elements do we have here? P. And here p minus 1. So p minus 1, p minus 1, p and 1. Total 3p minus 1 and plus how many are the inverse elements? Well, 3p minus 1 plus 3p minus 1, it will be 6p minus 2. So 6p minus 2 is our degree because that's the element, that's the number of elements in our generating set. And now we are asking how many vertices does our graph have? Well, the number of vertices of a Cayley graph is the number of elements of a group. So we are must check how many elements are in this group. Every element of the group corresponds to vertex of a graph. So since we have 13 elements in this group, it will give us 13 vertices. Since I mentioned here p times p minus 1, right? Because p elements in this group, p minus 1 elements in this group. Therefore, the order of the graph, the number of vertices of the graph is 13p times p minus 1. However, we want to have our result in terms of degree. Well, no problem, because degree is 6p minus 2, so we can easily express p in terms of d. So now the graph which we are going to construct, or actually which we already described how the construction works, has this number of vertices. So we constructed Cayley graph having this number of vertices. Again, d is related to p, so we can express p in terms of d. And then you are going to get this value. Well, we did show that the degree of this graph is the number mentioned here, which also is mentioned in the theorem in the previous page. Here. So we know that the degree is 6p minus 2, but we are stating here that this graph has diameter 2. We didn't yet show that the graph has diameter 2. That is the last, and often in these Cayley constructions, the main challenge to show that the diameter of that graph is really the number which we are stating. So in this case, if we want to show that the diameter of that Cayley graph is 2, we must show, as in the previous construction yesterday, that any element of the group can be expressed as a product of at most 2 generators. And again, it would be, maybe it would be repeating the same step. So I will show this to you only on a certain group of elements. So I'll show you how these elements can be expressed in terms of generators. So again, x1 is anything from the additive group. X2 is anything from the multiplicative group. And the last coordinate must be 7. So here I am covering p times p minus 1 elements. Maybe first don't focus on this part, because this part is actually just generalization of these 4 steps. After I express these 4 elements, I realized actually in the research paper, it's easy to just write it in general, because this is general way of writing these 4 elements. So I can express these 4 elements, this p times p minus 1 elements, p times p minus 1 elements, p times p minus 1, and p times p minus 1 plus plus plus. So all of them together give me 4p minus 1, and all of them are actually expressed here. If s and t is minus 1 or 1. So again, this one is just generalization of these 4 sets of elements. And how they are expressed, maybe I was talking last 3 minutes, you already checked everything. So, for example, this element can be expressed as b times element c, because this is the element b, this is the element c. We don't need to use any tricks with minuses, which are, let's say, used here. As you can see, if you multiply b and c for first coordinate being x1, and here the second coordinate being x2, maybe some of you are wondering why here x1 combined with 0 gives you x1, and here y1 combined with x2 gives you x2. Why is not 1 here or 0 here? Well, because first group is additive. So we are taking this plus this. The second group is multiplicative. Therefore, we are taking this multiplied by this. And the third group is again additive. Therefore, 3 plus 4 gives you 7. Well, next one, you are taking b to the power minus 1 because now we want the last coordinate here to be minus 3. Because if we want to get 1 here, here we wanted to get 7 here. Well, or we just try to cover all of them, because if we are using group Z13, we must make sure that our construction works if the last coordinate is 0, 1, 2, 3, 4, up to 12. Well, this way, combining generators B and C will work only for the last coordinate being 7, minus 7, 1, minus 1. So out of these 13 possibilities, we are going to cover only 4 of them by using generators B and C. As you will see in the next page, we are going to use some other combination of generators to cover different last coordinate. Here we are covering only 4 possibilities for last coordinate. Obviously, when I was trying to come with this construction, well, there were many other groups which I was using here, and of course I tried something else than finite fields, and this was just what worked the best. Okay, let's just quickly go. So let's say this one. So now inverse, but not to inverse to x1. Let's replace x1 by minus x1. Since minus x1 was here, since for x1 minus x1, for minus x1 we will have x1. Because I want to have nicely here x1, x2. I don't want to have some mess here. I want to have nicely x1, x2, so I can pick any element. Let's say it minus x1. Minus x1 will give me x1. This one was the same as here, so you can see again, x1 will be x1 plus 0, and x2 will be 1 times x2. And similarly, all the others. For example, here, c to the minus 1. Here I was taking c to the minus 1 of x2. Of x2, it was this one. So of x2 to the minus 1, inverse, it will come back to x2. Right? It will just, since for x2 we have inverse here, for this one we have inverse here. And same story, minus 3 plus minus 4 will be minus 7, and so on. And here again, x1 plus 0, 1 times x2 will be giving to x2. Similarly, but as you can see, in case you are combining generator of the form A together with generator of the form B, there will be a bit of some challenges. So it will be not as straightforward. You will have to do some more work here to get nicely x1 and x2. Again, these 4 steps combined can be expressed like this. So this equation contains these 4 elements expressed in a little bit general way. Actually, now when I look at it, I don't know if in the proof in the paper if I kept it in the general way, because I guess for the reader this would be quite confusing. Maybe I was just letting him know that this is possible, but let's rather write it in this way because it's difficult to check everything just from the general step. So here we are combining generator A of the form A and generator of the form B. But generator of the form A has, as you can see, we are working on 2 coordinates at the same time, because sometimes we need that A for something else, yeah? Because B and C is working on only on 1 coordinate, but A is working on both coordinates. So let's just check the first step. So what is AX2? It will be X2, X2, 1. You can see from the top what is there. In general, AX is XX1. So AX2 will be just X2, X2, 1. And now you might be wondering why we are using BX1 minus X2. Why not just X1 or not just X2? Because the effort is for that purpose that we want to have it nicely expressed in our form. Anything, and form. So therefore, if we are using these 2 generators, we are going to do this one, and the product of this one and this one is actually not a product because the first group is additive. Therefore, this one plus this one, x2 plus x1 minus x2, x2 will go out, and we have just x1. And the second coordinate is actually easy, x2 times 1, and the third coordinate is easy, 1 plus 3 will be giving you 4. Similarly here, we need it, why we are using it inverse, or here even, we are using two inverses. Well, we need to express also the element which has last coordinate -4. And if you want to get last coordinate to be -4, there is no other way only to use inverse to A and inverse to B, because then you will get -1 and -3. So again, the reason to get -4, there is no other way to get -4. Only use generator of the form A to the -1 and generator of the form B to the -1. That one will give you -1, -3, you will come to -4. And again, the tricks which I am doing here with, let's say, inverse of x2, and it will be actually multiplicative inverse to x2. But again, if we are following what mentioned there, you must just add minus in front of it. So again, minus additive inverse. And here, the second one is easy, and third one is -1. Similarly here, we must use this element. This is some element. Okay, we need to take minus this element, which will be this one, as if you are following b to the -1. And then again, if you are now adding this one to this one, you will nicely get x1. If you are taking x2 times 1, that one is easy, that one just x2. So actually the biggest challenge was working on the first coordinate to get beautifully x1 there. So this is just the diameter. Well, I showed you only 8 elements, but all the elements of the group, also the others, can be expressed. So finally, the diameter of this graph would be 2. Now, I want to tell you something also about directed Cayley graphs, because actually the undirected Cayley graphs, which I mentioned in the first part of my course, last 3 days, those are the main ones. But often researchers also study maybe problems which were less studied. So maybe if directed Cayley graphs, or in general, the degree diameter problem for directed graphs was studied less, there is a bigger chance you will succeed to find some result, because the problem is newer, less studied. So it's maybe worth to do some effort in this part. And if you succeed maybe to find something in the directed, maybe then you will get some motivation to study also bigger problems, let's say for undirected. So let me first define directed Cayley graph. So very similar. Elements or vertices of the graphs are elements of the group. But now edge will be directly. So now it's not edge between two vertices, but edge from one vertex to the other vertex. Edge from one vertex U to the other vertex V, if and only if there is a generator such that V is U times A. Or as I mentioned, between U and A, there is a group operation. So in case it's an additive group, it will be not U times A, but it will be U plus A. Okay, now we need to define also, because now we don't really have a degree in the same sense as in the previous undirected case. Now we have out degree and in degree. Out degree means edges which are going out from the vertex. And in degree means edges which are going in, so to the vertex. So let's say if I take something like this graph or this vertex, we are focusing on this vertex V, and we are studying what is the in degree and out degree of this vertex. Yes, in degree would be 2. In degree would be 2 because there are 2 edges going in, and out degree is 3 because there are 3 edges going out. Out degree would be 3. Well, if we are focusing on Cayley graphs or Cayley digraphs, Cayley directed graphs, then out degree will be always the same as in degree, and we will just call it degree. So maybe don't get confused. Let's say if I show you the next page, I think there is some example there. Yes, if you are looking at this graph. So as I mentioned, if for directed graphs in degree is equal to out degree, and we will call it degree, what is the degree of this graph or the degree of every vertex in this graph? Not. Let me just write it down. In degree is equals out degree is equals degree for directed graphs. What is in degree? There. Well, in degree is 2, out degree is 2, so the degree will be 2. So for directed graphs, be careful. We are not looking how many edges are touching this vertex. The degree for directed graphs will be how many are going out. The same number is going in, and the same number will be called the degree. So now the degree is not 4, the degree is 2. And now, what about this Cayley graph? It can be, it's a Cayley graph for which group and for which generating set. Maybe there are more possibilities, but the easiest group will be that as the cyclic group Z6 and the generating set. Can you tell me what do you think is the generating set for this graph? Well, 1, because we are jumping by 1 out the cycle, and the second generator is 2. So the generating set is containing 2 elements. 1, because we are going by 1. Well, depends how we denote the vertices. But if the notation for our vertices is this one will be 0, this one will be 1, the next one will be 2, 3, 4, 5. So if we denote vertices in that way, then the generating set is containing elements 1 and 2. Obviously, if we would denote the vertices the other way around, this one would be 0, this one 1, that one 2, 3, 4, 5, the other way around, then the generating set would be 4 and 5. And now we don't have to satisfy that rule which we had for undirected graphs. For undirected graphs, we had to have our generating set to be equal to x union x to the minus 1. So it had to contain inverse elements. Obviously, here it's kind of easier because we don't have to care about inverse elements. So again, for undirected graphs, we always had to care about inverses and include them in the generating set. For directed graph, this was for undirected. For directed graphs, we don't have to care about inverses. Maybe just check if you understand how to construct the Cayley graph, or if you are sure you understand, you don't have to write it down, but just try it. So try it. I will give you just 1 minute, and you can just try to construct Cayley graph for group which is Z4 times Z2, and the generating set which is mentioned here. While you are doing maybe your first attempts, I can just say some properties of this Cayley graph. So since the generating set has 2 elements, it means 2 edges are going out for every vertex and 2 edges are going in to every vertex, which means we call it a directed Cayley graph of degree 2, because in degree is 2, out degree is 2. And how many vertices does this graph have? Well, the first group is Z4 contains 4 elements. The second group, Z2, contains 2 elements. So we'll be. So the elements of this group will be the first coordinate can be 0, 1, 2, or 3, and the second coordinate is 0 or 1. So the second coordinate is 0 or 1. Let me keep here the second coordinate 0. The second coordinate 1. And the first coordinate 0, 1, 2, 3. 0, 1, 2, 3. And similarly on the other side. So the first coordinate from the group Z4, the second coordinate from the group Z2. 0, 1, 3. So these are the vertices of the graph. And now what about edges? Well, edge is going from the vertex ij to, now it's really directed. So from ij towards plus 3 here. So I plus 3. And what will be the other coordinate? J or J plus 1? J, right? Because first generator we are jumping by 3, but second coordinate we are keeping the same. And the second type of edges will be from ij to what? Now, first coordinate will be the same, and second one will be +1, right? So it will be a, I, and j plus. So as you can see, for every vertex, you must do this. You have 8 vertices. For each of them, connected with the, let's say this one is easier. Let's just first do this one. I connected to j. So ij connected to ij plus 1. So second coordinate jumps by 1. It's going this way, right? It's going this way. Going this way. Going this way, right? Because we are passing 1. Okay, let me, there is still something else what can be done there, but let me just now follow our jump to this one. Now we are plusing 3. So let's say, what about this one? 2 plus 3 is 5. What is 5? In Z4 it's 1, right? So we are doing this one, this way. 1 plus 3 is 4, but 4 is 0. 0 plus 3 is 3. Again, I plus 3. So 0 plus 3 will be 3. And again, 3 plus 3 is 2. We are doing. Similarly here, exactly the same, right? Do you think we are done, or do you think something is missing? Because it doesn't seem like out degree and in degree of every vertex is 2. We must also think from 0, 1, applying this one. If you put here 0 and 1, going to 0 and 1 plus 1, which is 0, right? Because 2 is 0, because we have group Z4 times Z2. Okay? So we must add these edges. And now we are finished. Now, for each generator, we have edge going out and edge going in. That's what you must have. For this generator, it will correspond to edge going in and out. For this generator, for every vertex, it must correspond to vertex going in and vertex going out. So we have this Cayley graph. Now, diameter of a Cayley graph. Similarly as for undirected graphs, the diameter of a directed Cayley graph is at most k, even only for every element of the group, or every element of the group can be expressed as a product of at most k elements of the generating set. If it's slightly unclear, it's very easy to have example and illustrate it on that example. So let's just, what is the diameter of this graph? Well, first, let's draw the graph. Maybe some of you can see it even without drawing, but let's rather illustrate it on that graph when we have it presented here. So Z9, it will have 9 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9. And what about edges? So let's have vertices 0, 1, 2, 3, 4, and so on in that way. 5, 6, 7, 8. So since we are using group Z9, therefore Z9 contains 9 vertices. Z9, not 9 vertices, 9 elements. Group Z9 contains 9 elements, 0, 1, 2, up to 8. Again, element of the group corresponds to vertex of a graph. And if the generator is 1, we are jumping by 1. Directed edge. Directed edge from 1 to 2. Directed edge from 2 to 3. And so on. Generator 1, we are jumping by 1 with directed edges. Generator 3, we are jumping by 3 with directed edges. So every element I, or every vertex I, there is a directed edge to vertex I plus 1 and I plus 3. To I plus 1 and to I plus 3. Well, I plus 3. 0 is going to 3. 3 is going to 6. 6 is going to 0. Are we done? No, because what about this vertex? 1 must go to 4. 4 to 7. And 7 back to 1. Similarly, 2 to 5. 5 to 8. And 8. 8 to 8. 8 plus 3. 8 plus, yes, 8 plus 3 is 11. 11 multiplied by 9 is 2. So now we have this graph. And now we want to know what the diameter is. Well, it's enough to focus on one vertex. Let's focus on 0. And we are studying which vertex is furthest from 0. So let's write down the non-identity elements of the group. 1, 2, 3, 4, 5, 6, 7, 8. And they can be expressed in terms of generators. What are our generators? Now only 1 and 3. Not 1 minus 1, not minus 3. Only 2 generators, 1 and 3. As I mentioned, if it's directed graph, we don't care about inverse. They are not used. So we are expressing all these numbers only by plussing 1 and 3. Okay, 1 is the generator, just 1. 3 is the generator. From 0 to 2, we get by generator 1 and generator 1. So this is by using 2 generators. 4 is 3 plus 1 using 2 generators. 5 is 3 plus 1 using 3 generators. 6 is 3 plus 3 using 2 generators. Do you have now guess what will be the diameter? The diameter will be 4. Because 7 can be expressed as with the help of 3 generators, but 8 with the help of 4 generators. Since 8 can be expressed with the help of 4 generators, but not less, therefore the diameter is 4. You need to take 4 directed edges to reach 8 from 0. There are many ways how you can walk. You don't have to go 3, 3, 1, 1. You can start slowly 1, 1, and then 3 steps, 3 steps. But there is no way to reach 8 from 0 by less than 4 generators. 4 is the smallest number, therefore the diameter of this graph is 4. Now the degree diameter problem for directed graphs, the definition is similarly defined as for undirected graphs. We are looking for the largest possible number of vertices. So for the largest possible graph in a directed graph of given maximum degree and diameter. If we are defining this problem for Cayley graphs, we do not have to mention the word maximum. Why? Because for Cayley graph, the degree of every vertex is the same. But if we are studying general graphs, maybe the largest graph which you find doesn't necessarily use every vertex maximum degree. Maybe one vertex, or maybe many vertices will have degree whatever, 24, but one vertex will be having, or a few vertices will have degree 23. But for Cayley graphs, the word maximum is not necessary because Cayley graphs are regular. Now, again, some simple results for directed graphs. Now, again, Moore bound. So, Moore bound for directed graphs will be slightly different than for the undirected graphs. Let me just illustrate why. So, again, similarly as when I was showing the Moore bound for the directed graphs, undirected graphs, I start from one vertex. And I'm studying how far can I get from this one vertex? Well, in the first step, this one vertex has degree D, which means they are at the most D vertices. of distance 1. First vertex, second vertex, at most d vertices. So we are starting from 1 and now plus d. So the first step is the same also for directed and also undirected. But plus, second step will be already different. Because in the second step, previously when we studied undirected graphs, this vertex was already connected to 1. So in the next step, we could have at most d minus 1. Because this is connected to 1 here, it can be connected to at most d minus 1 in the next step. But not for directed. This is in degree for this vertex. It can still have d outer degrees or d vertices which are connected in this level. So it will be not plus, if you remember for directed graphs, it was plus d times d minus 1. Now it will be plus d squared. For every vertex, you will have d possibility. So you will have d here, and in the last step, plus, or in the third step, again, this vertex can be connected to other d by directed edges. So let's say if the diameter would be 3, the Moore bound would be 1 plus d squared plus d to the power 3. But I mean, this is again only theoretical maximum, because if you want your graph to really have diameter 3, then you must start connecting these vertices back this way to something to achieve the diameter 3. Because now you are just at the beginning of the process of constructing the graph. These vertices don't have any connections back. So we can't state that the diameter is 3 yet. We will have to do a lot of effort here to construct some graph which every vertex has in degree and out degree. Which graphs are again the simplest, which are Moore graphs, or the now Moore digraphs, since we are studying it for directed case. So, complete diagrams. How do they look? Maybe again try in your notebook. What is the complete graph or complete directed graph with 4 vertices? How does it look? Because now we are working with directed edges. So, do you think this one is correct or not? Well, if you look at the directed complete graph, they have degree d with d plus 1 vertices. Since I'm studying it for 4, d plus 1 vertices will be 4 vertices, d plus 1 vertices, which means out degree and in degree must be d, which means each vertex 3 must go out and 3 must go in. So this is by far not enough, right? Because this graph also wouldn't have diameter 1. It says complete graph must have diameter 1. Diameter 1 from every vertex to every vertex, you can get by one directed edge. So for every 2 vertices, you must have edge going in and edge going out. For every 2 vertices, you must have edge going in and edge going out. So this one is the complete graph with 4 vertices for diagrams. As you can see, pick any vertex and any other vertex, and there will be directed edge going from that vertex to the other one. So this is the Moore diagram of diameter 1. And another easy example is directed cycles. Directed cycles, maybe we can also check that do complete graphs really satisfy the Moore bound? Because if they are really Moore graphs, it means the number of vertices in this graph is equal to the Moore bound. Moore bound is here. We need to replace k by 1. If you replace k by 1, it will be only d here, which means you must stop here. It will be not plus d squared plus d to the power 3, because the last one is d to the power 1. You stop here. So it really has 1 plus d vertices. D plus 1 is 1 plus d. So you stop here, and this is the number of vertices of a complete graph. Here we are saying directed cycles with k plus 1 vertices for Now, general diameter, any diameter, but degree 1. So again, if we want to check if the bound is satisfied here, if they are really Moore graphs, well, let's replace D by 1 now. And let's keep K to be general. If you replace D by 1, you will have here 1 plus 1 plus 1 plus 1 plus 1 up to the end again plus 1. So how many ones do we have? Where here is D to the power 1, right? So here we have K times 1. 1 plus 1 plus 1, K times. K times plus another 1. So K plus 1 times that 1. So it's really K plus 1. And degree is 1, which means out the degree and in degree is 1. We have here example of a cycle. If you remember for undirected graphs, even cycles were not Moore graphs. Let's say we took this graph for degree 2 and diameter 3. It was not a Moore graph because it didn't satisfy Moore bound. And there was another graph which had the same parameters but had more vertices, which was the odd side, having one more vertex. So not 6 vertices, that's not a Moore graph, but the one which has 7 vertices and is 7, that was Moore graph for this parameter. Now, what do you think? Is this graph a Moore graph or not? Yes, because for directed graphs, every cycle is a Moore graph. This one is now for the diameter equal to what? The furthest vertex is from this vertex is this one. And to go from this vertex to this one, it will take you 5 steps. So the diameter of this graph is 5. From this vertex to get to the next one is 5 steps. However, when you were having undirected cycles, the one which was furthest from this vertex was not its neighbor. At the beginning, I think you were confused. When I gave you a cycle with 100 vertices, sometimes you were guessing that the diameter is 99. That would be true for the directed because you can go only one direction. But the furthest vertex in undirected graph for this vertex will be the one which is on the other side. So you will be going somehow to the one which is the furthest. And just I want to give you at the end some easy example. So degree diameter problem for Cayley diagrams. I just want to define it. I'm not going to introduce again some proofs for this directed problem. So again, the problem would be looking for the largest number of vertices in a Cayley graph and directed Cayley graph of given degree. As I said, we don't have to say maximum degree because every vertex has the same degree. Therefore, we are just saying of degree and diameter K. And for example, the value of C22, the largest possible graph which you can construct for degree 2 and diameter 2 is a graph with 6 vertices. And I want to leave this last example as a small problem for you to draw it. Maybe it will be quick, maybe it will take you some time. So the question is, draw a graph which is scaly and which has out degree and in degree 2 and which has diameter 2 and which has 6 vertices. And you can also tell me for which group it is possible to construct such graphs. So I think it will be not such a huge effort because it has only 6 vertices. And anyway, you can tell me your answers also next week because I'm still here next week. And if you have any questions, we can still discuss anything what you wish. So thank you very much for your attention in the last 4 days.
Thank you very much for your nice lecture. Please, audience, from any question from anyone, our discussions.
So, I guess people also study like bigger groups here, and
Yes, similarly as for the undirected case. Also, the directed case is studied also for special groups, but as I mentioned, it has been studied less. So, so maybe there is more space for research in this area.
Any other question or comments? So thank you very much. And this is the, oh, sorry, please. One question from. Okay, you can ask.
Are there any results of other graphs other than cyclic?
You mean for directed or undirected case, or for both?
Directed problem.
Yes.
For any graph.
You are saying not clearly necessary.
Thinking that is a problem for Cayley graph. Any
Cayley graph.
Not cyclic.
Not cyclic or not necessarily abelian. Yes, there are results. Also, I have results in that area. And actually, what is very useful in this research problem, there is also a survey paper containing all the results. And maybe one generalization which I didn't mention, also authors already started to study this problem for hypergraphs. Okay, so yes, there are results for directed, undirected, graphs which are not Cayley, maybe graphs which are Cayley, graphs which are Cayley of cyclic groups, but maybe some other stream which is also maybe a little bit less studied is studying it for hypergraphs, because we know that in a normal graphs, H is collection of two vertices, but hyperedge means that hyperedge will not contain only two vertices, but let's say we can study hypergraphs of, let's say, which are, let's say, 5 uniform hypergraphs, which means every edge will contain of 5 vertices. It will be an hyperedge. So maybe this is also another interesting, because you were asking about some variations of the problem, if it was studied for this class or this class. So the class which was studied quite little is hypergraphs, means you will not have edges connection two vertices, but you will have hyperedge, let's say, connection of K or 5 vertices. You can just pick some number. If you take your K uniform hypergraphs, or let's say your hyperedge to be just of having 2 vertices, is hyperedge having 2 vertices, that will be just graph. So graph is a special class of hypergraph, and so hypergraphs is another set of objects which can be studied for the degree diameter problem. Yes, I can definitely send you survey paper. In case you just, maybe I can just tell everyone, there are 2 authors of this survey paper, and one author is called Miller, and one author is called Sheeran. And I now don't remember the title of the paper, but it was published in, I think, Electronic Journal of Combinatorics. And anyway, if you Google degree diameter problem survey, probably will find it. But if not, even today, you just send me email. My email address is very easy. My name dot my surname @gmail.com. So my name you probably know from the presentation. Again, my name, first name dot my surname @gmail.com. I guess in Pakistan this would be impossible because there are too many Mohammeds and so on. But my surname, it has about maybe 50 people in the world, and my first name and surname only 2 people in the world.
Thank you very much. So this is the end of the session, and thank you all of you, and have a nice weekend.